In our previous video, we defined the binomial distribution and looked at its probability generating function. So given a little bit of information and a check of a few assumptions, we can actually find probabilities of many, many events very, very efficiently. And we learned also how to calculate the mean of a binomial distribution as well as the standard deviation. So let's look at an example where we'll learn to set some of this stuff up. Approximately 70% of statistics students do their homework in time for it to be collected and graded. Each student does homework independently. Okay, so we're already seeing that 70%, there's a probability of success here of, in this case, doing homework, and it kind of is a success, right? And then 30% fail to do the homework. So it's literally success and failure, but it doesn't always have to be that way. Each student does homework independently, so every student is independent of the other. In a statistics class of 50 students, what is the probability that at least 40 will do their homework on time? Students are selected randomly. Okay, before we get to that question, let's look at a few things. This is a binomial experiment because there is only a success or a failure. There are a fixed number of trials, and the probability of a success is 0.7 for each trial. If we are interested in the number of students who do their homework on time, then how do we define x? Well, x equals the number of students in a group of 50 who do their homework. Now, we won't list them all out, but there are 51 possible events here. 0 students do their homework, 1 does their homework, 2 do their homework, all the way up to 50 doing their homework. So there's 51 different values for R, the number of successes that we get. So this would be very cumbersome to try to lay out completely. What value does x take on? Well, it takes on any number. We'll write it like this: x, the random variable, is in the range from 0 all the way up to 50, and it has to be an integer. So x takes on integer values only. You can't have 1.5 students. What is a failure in words? Well, it's the event in which a student fails to turn in homework. To turn in homework on time. And if p plus q equals 1, then what is q? Well, this is just kind of goes back to harp on the notion that q is equal to 1 minus p, because when you add together the probability of success and the probability of failure, you get 100%. So this is another way of seeing that if you have 2 events, one that has probability p and one that has probability of q, in our case, p is 0.7, that means that q is going to be 1 minus p, which will be 30% in our case. The words "at least" translate as what kind of inequality for the probability question, p of x? Well, at least means 40 or more, so this will be greater than or equal to. Okay, well, how do we actually calculate this? If we did this, we would have to find the probability that x is equal to 40, add to that the probability that x is equal to 41, and we would have to add up all of these. Well, there's 50 students, so the highest that we could have, the probability that x is equal to 50. So given that in our situation, p and q, p is equal to 0.7, Q is equal to 1 minus that. That's the probability that a student doesn't submit on time. We have N equals 50 students, and these are the different values of R. So for example, to calculate the probability of 40 students submitting their homework on time, that would be 50 combination 40, N combination R, times P to the R, 0.7 to the 40th, times Q to the 50 minus 40, which means you have 40 students all submitting on time. You have 10 students who don't, 30% chance of that. And then you would need 50 combination 41 times 0.7 to the 41st power times 0.3 to the 9th power, all the way up to, you would have 50 combination 50, 0.7 to the 50th times 0.3 to the 0. Remember, 0.3 to the 0 is 1, so that factor will not come into play at all in this calculation. Well, this is still a cumbersome calculation. It requires 11 quantities to be summed together. We'll show you a way to do this neatly. One very nice calculator at the time of the creation of this video is GeoGebra, GeoGebra.org, O-R-G, or you can Google it and you can see GeoGebra.org. There are many different types of calculators in here. One of them is a probability calculator, and I think we can access that with the calculator suite. Let me make sure here. We want to have the let's go to GeoGebra Classic, and off in the menu we can select View and we can select Probability Calculator, and we'll just uncheck these other ones, and there are other probability calculators out there. This one will allow us to select the distribution that we want to work with. So we'll go to the drop down here, we'll select binomial, and then we can enter in our number of trials. So here we have 50 students. The probability that they complete their homework is 0.7. And in here we can actually compute individual probabilities by just either highlighting, you can click on a used to be that you click on a bar, but if we want to know the probability of having 40 students all complete their homework on time, we see that that probability is 0.0386. But if you click on one of these and press Shift and then click the last one, I think we can maybe even, there we go, we can even highlight it here. You can see that that adds all of them up, and down here it says the probability that X is between 40 and 50 is 0.0789. There's about an 8% chance that you get between 40 and 50 students all submitting their homework on time. And as an instructor, I can say, yeah, this seems to be about accurate. There's not a high likelihood that somebody doesn't do it. And you can also come back in here and you can select different ranges and see that the area corresponding to all of these bars, the probability of summing from 0 students all the way up to 50 students is 100%. Now, we can also see the mean here. So on average, we would expect 35 students to do their homework submitted on time with a standard deviation of 3.24. So that's going to mean that around that mean, you'll probably have somewhere between, on average, 31 and 39 students submitting their homework on time. Great, so we've answered our question. We said that was about 0.078 or about 0.079. So this comes out to about 0.079. Now, just to verify that the calculation of the mean is n times p. Okay, so in our case, we have 50 students. Probability of completion is 0.7, and lo and behold, 70% of 50 students would be 35 students. And then the standard deviation is the square root of n times p times q. So that's going to be the square root of 50 times 0.7 times 0.3. And that comes out to be about 3.24. So we're going to expect to see in general somewhere between about 32, we said 32 to about 38. And you can see that that does encompass the majority. That covers about 80, 81, 82% of students. And if we kind of bump that down a little bit more to account for the rounding, we're looking at about 84% of students. So on average, we would expect most students to be within one standard deviation of the mean. We'll take a look at one final example here. And in this example, according to a Gallup poll, 60% of American adults prefer saving over spending. Let X equal the number of American adults out of a random sample of 50 who prefer saving to spending. So we can see that we have two preferences. We have two possible outcomes. We have an outcome of saving and an outcome of spending. So we can think about this as a success. We can think about this as a failure. Now that's not, we don't get to define what the failure is. We're just focusing on the random variable defines a success to be people who prefer saving. But, you know, you could argue that spending is good, and maybe your viewpoint is you don't need to save. So failure and success are really just kind of these words that we attach to these outcomes. And success is whatever you define X to be counting. We see that there's a constant probability, right, that any given person has a 60% chance that they will prefer saving, independent of others. So we assume that, you know, your choice does not affect somebody else's choice when saving versus spending. And it could, right, because our kids maybe would prefer saving if they learn that we really prefer saving. We're kind of just assuming that this is a random sample of 50 people. So they're probably not going to be connected. Probability distribution of X is a binomial with n equals 50 people. Depending on what order we want to list these in, if we list P first, it would be 0.6. N is 50. Use your calculator to find the following probabilities. The probability that 25 adults in the sample prefer saving over spending. So what's the probability that X is greater than or equal to that 25? Oh, 20, it's exactly 25. So this will be, what's the probability that X is equal to 25? And if we wanted to set this up, we would have n combination r. So from 50 people, how many different ways are there for 25 of them to prefer saving? Times the probability of those events, which will be P. In our case, 60% chance that you prefer saving 25 times, and then 0.4, which would be the probability that somebody prefers spending instead of saving, to the 25th power. Now I'm going to go ahead and just update things in here. We have, the only thing that changes is this 0.6 here. And you can see this nice, beautiful, almost bell curve-like shape. We'll come back to that in a future video. And what we want to look at here is the probability that exactly 25 people prefer to save over spend. Well, that's equal to 0.0405, which is equal to about 0.04 or 4%. So 4%, there's a 4% chance that in a group of 50 people that you happen to get 25 of them who prefer saving over spending. Now that's a small chance, right? But keep in mind that there are 51 possible outcomes. Each one of them accumulates to the 100%. The probability that at most 20 adults prefer saving, so at most means less than or equal to 20. Okay, so we'll come in here and we'll say, that could be 0 all the way up to 20 people. And you can see that this is a very, very, very small chance, because in 50 people, there's a 60% chance that they prefer saving. N times P means that on average, 30 people in a group of 50 should say they prefer saving to spending. There's only a 0.0034, which is about 0.34% of people, or 0.34% of the time in a group of 50 people would we expect that 20 or fewer of them prefer saving. Okay, so we expect a lot more than that, right? Because on average, we get 30. The probability that more than 30 adults prefer saving, x is greater than or not greater than or equal to greater than 30. So I could write greater than or equal to 31. And so that will mean that I have to go from 31 on up. So all of those bars get their probabilities get added together. You get about 0.4465. It's equal to 0.4465, which is equal to 44.65% of the time. Now, just because the average is 30 doesn't mean that 50% of people above the average and 50% of the people below the average, that doesn't necessarily hold true, because this distribution is not perfectly symmetric. You can see that the bars on the right tend to be a little bit higher than the bars on the left. And so those probabilities are not all perfectly symmetric. They're not all the same. So that comes out to close to 50%, but not exactly. Using the formulas to calculate the mean and standard deviation. So we already have those, n times p. So you have 50 people, 60% of them we expect to prefer saving over spending, which will be 30 people. And sigma, which is the square root of n times p times q, is going to be the square root of 50 times 0.6 times 0.4, which comes out to about 3.46 people. And once again, what that means is that you should have realistically somewhere between about 26 and 34 people. I'm rounding to approximately 4. And we should see that if we looked at the probability of having somewhere between 26 and 34, that should account for a big majority of, and it does. It's about 81% in this case. So the bulk of people should be within about 1 standard deviation of that mean. Great, so there we have it. So that's working with the binomial distribution. I just want to point out one more thing. Notice that these are like coin tosses. Saving, spending, heads, tails. It's just a unfair coin in that it's 60% for heads and 40% for tails. Back up here, same kind of idea. We have students who submit on time and students who do not submit on time. Heads, tails. 70% chance for heads, 30% chance for tails. So a coin toss experiment is the perfect kind of exemplar for this binomial experiment that we're dealing with here.